Hey everyone, myself Bhavya Goyal, a student at IIT Gandhinagar. I welcome you at CodeChef and let's have a look at this question. So yeah, today's question is perfect matching. In this question, Chef constructed a tree with n vertices with the following process. So he initially generated a random array of size n minus 1, where 1 is less than equal to p of phi is less than or equal to I. So every element p of I is less than or equal to the index it is on, and all the possible arrays are equally likely. So he's generating a random array with all the arrays as equal likely. Now he creates a tree using this array with the root vertex labeled as 1. So the root is labeled 1. And for each I from 2 to n, he adds a vertex labeled I to the tree connected with an edge to the p of I minus 1. So for example, if this is our I and this is our p of I, then notice here that each of p of I is less than or equal to I, right? Now what we'll do is the root 1, this node 1 is nothing but the root. Node 2 will be connected to the this node 1. So we'll connect them up. Node 3 will be connected with node 1. Node 4 will be connected with node 2. Node 5 will be connected with node 4. And node 6 will be connected with node 3. So this is the tree formed if our random array generated was equivalent to this. Now, we need to find the probability that this tree has a perfect matching. Now, what do we mean by perfect matching? So by perfect matching, we mean that we choose a subset of edges such that each vertex appears exactly once. So, for example, the perfect matching for this tree could be we choose this edge, and this edge. So these two vertices are exactly visited by this one edge. These two vertices are exactly visited by this one edge, and these two vertices are visited by exactly this one edge. And for a tree, there can exist at most one perfect matching only. Well, I think this is a property which is true for all the trees. If we just verify this property once, we will not need that property in this question, but you can just verify it once. So yeah, this is one perfect matching for it. That is, we select this edge, these two, this edge, and these two are selected, right? Now we need to tell the probability that the random array that was generated or the random tree that was generated has a perfect matching. So it would be much more clear once we see this sample input. So if we have just one node, can we select any edge for a perfect matching? No, right? Because there is no edge. So the answer is 0. If the input is 3, we have two nodes. One is 1 and the other is 3. And there is 1, 2. Irrespective of how we arrange them, if we select this edge, one node will always be left out, right? So there won't exist any perfect matching, right? Now, what if n is 2? So we can select this one edge, and this is a perfect matching, right? So the answer is 1. Now, what if n is equal to 4? So if n is 4, then these are the 6 possible trees that we can generate. And notice that this has a perfect matching that we select these two. And using this edge, we select these two, right? So this is one possible edge. This also has a perfect matching by selecting these two and these two, right? This also has a perfect matching by selecting these two and these two. And this also has a perfect matching by selecting these two and these two, right? Now notice here that these two are invalid because if I select these two, I cannot select these two in any possible way. If I select these two, I'll not be able to select these two. So it will be invalid. And by invalid, I mean that it won't have any perfect matching. And similarly, this also won't have any perfect matching, right? Because I cannot select any two edges such that it has a perfect matching, right? So in total, there are 6 possibilities and 4 of them are valid. So the answer is 4 by 6, but we need to print it modulo this number. So we need to print it modulo this number. So if we'll print 2 by 3 modulo that number, we'll get this as our answer. So yeah, this is pretty much the test case, and I hope the problem is pretty clear now. Now let's move to the solution. So let us begin by calculating that what are the total number of trees that we can get. So for example, so we just want that P of I is less than or equal to I for all i's in between 1 less than equal to I less than equal to n minus 1, right? Now let us say our i's are like this and our p is like this, right? So for first input for I equal to 1, it has to be 1, right? For I equal to 2, p of I can have two values, 1 or 2. For 3, it can have three values. For 4, it can have four choices. And in total, how many possibilities can we have? 1 into 2 into 3 into 4 dot n minus 1. And this is nothing but n minus 1 factorial, right? So in total, we can generate n minus 1 factorial random arrays, right? And this is just to illustrate on how we'll be creating a tree. So one is our root node, two has to be the parent, the one has like the two has to be child of one, right? For three, we have two options, either connect three with this two or connect this three with one, right? So these are the two possibilities which three can have. For four, we can have four possibilities based upon which tree we choose. So if this was the tree, we could have added a 4 over here, a 4 over here, a 4 over here. Or if this was, let's say, the tree, we could have added a 4 over here as well, right? So in general, the total number of trees we'll be having is n minus 1 factorial, right? So now if we can calculate the perfect matching trees, the number of trees that have perfect matching, and if we divide it by this n minus 1 factorial, we'll get the probability that on choosing a random tree or random array, what is the probability that it is a perfect matching or it has a perfect matching, right? Now, how do we count the perfect matches? So first of all, a very trivial observation is if n is odd, the answer is straight away 0. Why? Because we need to pair up the edges, pair up the vertices, right? And one edge pairs up two vertices, right? So for any tree to have a perfect matching, it must have even number of vertices. Otherwise, one node will always left unpaired, right? So if we select this edge, this will get paired, but this will always remain unpaired, right? Now, what if n is even? So if n is even, we'll define that the number of trees with perfect matching. So this f of n is nothing but a recursive function, which will calculate that what are the number of trees with perfect matching such and which has a size of n. And we know that n is even initially, right? Initially, Rn is even. Would we have to calculate this if it is odd? We'll see it right? So, okay, we know that n is even, and this 2 will always be a child of 1, right? Because of the way we are generating the trees, right? This first value would be always 1, and this 2 will always be, like this 1 will always be a parent of this 2, right? So we know that our tree with n greater than or equal to 2 will always have some structure like this, right? We'll have a 1, this 1 will be attached with a 2, the 2 will have a subtree, and this 1 could also have a subtree of size greater than or equal to 0, right? Now, what do we do? How do we calculate it? Right. So first of all, seeing the constraints, I did not discuss them. So seeing the constraints, we can say that n square could work, right? And so we could think of some kind of DP to calculate our answer, right? Because we know that okay, f of n stores this. And if we can just figure out some transition, or if we can figure out some or break down this f of n into some two smaller tasks, then we can ask our recursive function to calculate the answer for those smaller tasks, right? So what we'll do is well, let us say that this tool has some subarray size, subtree size of S. I'll change this to subtree. Right. So let us say that this tool has some subtree size of S. Right. Now, what if S is even? If S is even, we have just broken down this into our two subtasks, right? One is this subtree, and the other is this subtree. Both of will have even size, right? This will have even size. This will also have even size because n is even and s is also even, right? So this is even, so we subtracted an even from even, so it would be this part will also be even, right? Now we know that now all we are asked to do or all we are left to do is calculate that what is the possible answer for the smaller subset, right? So what we are doing is we had a bigger n, let's say the n was 10. We shortened it down to let us say a size of 5 and a size of 5. Sorry, a size of 4 and a size of 6, right? And now for this 4 size tree, it is independent of what initially we had, right? So we can just ask our recursive function that can tell me the answer, that what is the number of trees with perfect matching I can get, such that my total number of nodes is equal to 4, and similarly my total number of nodes is equal to 6. Right. Now, okay, what are the total number of trees that we can get for a particular S? That would be n minus 2 choose s minus 1, because we total in total this 1 is fixed, this 2 is fixed. We still have n minus 2 vertices left, and we can place any of the s minus 1. So this has a size of s, this has a size of s, so we can place any of the s minus 1 vertices over here. So we'll choose s minus 1. So this is the total number of possible vertices we can send to the subtree, and the number of possibilities for this would be fixed because we have already selected for this. So we have selected the number of vertices we'll send to this subtree times the f of s, that is how many possibilities will exist for this much part of our tree, times f of n minus s, that is the number of possibilities for this much part of our s. And if we take the summation of this over all of these s, we'll get our answer for this f of n, right? Now this was the case when s is even. Now what if s is odd? Right, now what if s is odd? Right. So if s is odd, then these two will have to be paired up, right? Why? So I'm claiming that if my S is odd, these two have to be paired. Now I would like, it would be better if you just pause this video and just think about it once for yourself. But yeah, now what if S is odd? So if S is odd, that means this much subtree is odd, right? It has a size of odd. And if this two is already not paired up with anyone, then I'm asking for a case where my total number of vertices is odd and I want to pair them, which is not possible, right? Which we just discussed above over here, right? But what if these two are already paired? What if I've already paired them up in a matching, and now my subtree would have a size of even, right? Like this subtree would have a size of even, and this subtree would also have a size of even, right? Now, like what basically I am asking my function, my recursive function is that, okay, if S is odd, I'll pair them up, no issues. I'll just pair them up, just calculate the answer for this such that this root vertex is already paired up. And for this, such that my root vertex is already paired up. So this vertex is paired up, this vertex is paired up. Now tell me the answer of how many number of perfect matchings can I get? All right. And this thing would still remain exactly the same because I still have exactly these many possibilities to choose from. But in that case, my f of n is going to be odd, and I need my function, my recursive function, to calculate the answer. If n is odd, and whenever n is odd, that means the root is already paired up with some other vertex above it. Right. Now, how would we calculate if n is odd? So for that, notice that, okay, I'm using 1, 2 again over here because the convention of these numbers or these labels do not really matter, because this size n is independent of what we had earlier. So this is equivalent to saying that, okay, I calculated my answer for this. Now I need to calculate my answer for this subtree as a new n, and I can just label them again as 1, 2, 3, dot, 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 whatever I want, right? Because that won't really matter. Now this is 1, this is 2. And notice that this one would be obviously different from what we had already done by some parent, right? By some parent recursion. Anyways, so this one is already paired up earlier, right? Now notice here that n is odd, right? And this is over here, this s denotes the size of this subarray, the subtree, whatever it is. Now, can we ever have this size of this s to be odd? Right? S is odd. S is odd. What if it is odd? If S is odd, that means this much subtree is odd size. And if this much subtree is odd size, I cannot pair this two already with anyone because the parent is already paired, right? And that means I already have n vertices. I'm asking my recursive function to calculate for n, but this n is odd. And this root node is not already paired up with anyone, right? So I cannot have any possible tree with that cells, right? So this S must be even. This S has to be even. Now, what if S is even? So if this S is even, then that means this subtree has some even number of vertices. This will also have some even number of vertices. This will still have odd number of vertices, but I'll ask my recursive function to handle that, right? But in general, my n is getting broken down into s and n minus s, which are shorter. And how many possibilities do I have again? I still have to choose s minus 1 because these two elements will be fixed. S minus 1 elements for this from a total of n minus 2 elements. So n minus 2 choose s minus 1 times f of s. That is how many possible perfect matchings I can get from this subtree times n minus s. That is how many I can get from this subtree. Right. This case would be again odd because our n is odd and s is even. So this still would be odd. Yeah, this case would still be odd, but it is still fine. My recursive function would handle it again. And if this is even, that is again simple. My recursive function will handle that. And that is pretty much how it will work. Now our base case, what if n is equal to 1? That means that basically means that we are just left with one vertex and it is already paired up with some other vertex earlier, right? Because we are sending an odd case if and only if the root is already paired up. Otherwise, we are not sending the case of odd, right? So that means this root is paired up. Now there is nothing to do further. So there's just one possibility that we can get. So the answer is 1. So this is pretty much the whole solution. This can be implemented with the time complexity of n squared using Murphy. And now let us see the implementation for this. So let us begin by seeing the implementation in C++. I have used quite a lot of lambda functions in here, which I'll explain. So before that, we have defined the mod. We have defined the binary exponentiation function using this lambda function. So what it does is it it has a format. So it will take function, it will return an integer or a long, and it will take the argument a and n. And this is our whole function. We have defined, yeah, this is just the binary exponentiation after that. We have defined this capital N to be 1e5 plus 10. We are taking in the factorial, calculating factorial for all of them. We are calculating the inverse of factorial for all of them. This is our n choose r function, which will return us the n choose r. We'll begin by taking an input of all the test cases. We'll take an input of n. Now this is our recursive function. So over here, we are defining a function, a lambda function, which will return an integer and take an argument of an integer, that is a single integer n, and it will return an integer. So if n is 1, our base case will return 1. If dp is not minus 1, we'll return the dp. We have defined an answer to be 0. We'll go from s equal to n minus 1 to 1. And we'll subtract 2 if n is odd and 0 and 1 if n is even. The number of ways is f of s times f of n minus s times the n choose r, which will add to our answer and return this answer. This is nothing but an iterative version. You can just uncomment it and try it yourself. It's pretty much the exact same. In the end, if our n was even, we'll print our answer. Otherwise, we'll print 0. And this is all for the solution in C++. Now let us see the solution in Python. So we'll begin by we'll define the mod and the maximum n and the factorial array. This is our binary exponentiation function. We'll pre-compute all the factorials. We'll pre-compute all the inverse of those factorials. We'll define a function to calculate n choose r. We'll take in the input of t. We'll run a loop for each test case. We'll take in the input of n. We'll define a dp array with 1 initially. We'll run for all the possible values of s. Now, number of ways is dp of s into dp of I minus s times the number and choose r of I minus 2 times from s minus 1. That is the possibilities to choose I minus 2 from s minus 1. You can also change this variable from I to n to match the convention we used in the tutorial. Now, if this n is even, we'll print our answer. Otherwise, we'll print 0. And that is pretty much the whole solution. The time complexity of both the solutions is big O of n square. And that's it for this video. I hope you liked it. Thanks. Bye-bye.